Okay, so we're moving on from the study of the linear algebra of matrices and vectors and into the significantly more confusing territory of the linear algebra of functions. So the goal here, our goal for the next section of the class is to make this make sense. So essentially what we're going to say is, if we're looking at a differential equation like y double prime minus 2y minus 15y is equal to 18e to the 6x, I want to be able to look at that thing and be able to extract the full set of solutions to it. So I'm going to tell you that this is the study, this particular one is a second order equation because there's a second derivative inside of it. It's linear for reasons that I will define later. And that the general solution to this, I'm going to tell you what the solution is. So the general solution to this equation looks like y is equal to 2e to the 6x plus c1e to the 5x plus c2e to the minus 3x. So every single solution to that differential equation has that form. So this is called a general solution. And so our objective is to figure out a class of differential equations that we can study and a set of tools that we can use to figure out what these solutions are. So some things you should notice here are, why are there two of these pieces that have coefficients attached to them? Is there a difference between this bit that does not have arbitrary coefficients and this bit that does? And then the longer term question is, how do you know that's every solution? And how did you come up with that besides the fact that it was an example that was written down in somebody's notes and you just wrote down what the solutions were, right?
Is that a 5?
It's a 5. It's right here. Okay, so this is the sort of body of equations that we're going to be studying over the next couple of weeks. So in particular, we're going to be studying what are called linear higher order differential equations. Okay, the first observation that I'm going to make here is that I could write a different problem that was related to this problem. It looks like this. Y double prime minus 2y prime minus 15y is equal to 0. And that actually turns out to have solutions that look like y is equal to c. So if you actually write down two different solutions, y1 is equal to e to the 5x, and y2, you know what, I shouldn't do it that way. I should give you this example instead. Let's look at y double prime plus y is equal to 0. That's an equation you don't have to guess at. You can actually just tell me what the solutions to that are. A function that when I add it to its second derivative, I get nothing. Sine of x is, okay, so y1, there's definitely a solution. Can you think of any others? Cosine does it too, right? Okay, now, because of the nature of solutions to differential equations, if I add those two things together, I'm going to get another solution to the differential equation. Right? I am. So, how do I know? So here's a linear algebraic question for you. I would like to say that y is equal to c1 times the sine of x plus c2 times the cosine of x is the full set of solutions to y prime prime plus y is equal to 0. If I found two of them, I might have the suspicion, or in about 30 minutes you'll have the theorem that says second order linear equations have two-dimensional solutions, two-dimensional space of solutions. If I have got two solutions, and I'm saying I would like to show that the general solution is equal to linear combinations of those solutions, that's like another way of saying the solution space of y double prime plus y is equal to 0 is two-dimensional. And it sure would be nice if that was equal to the span of the function sine of x and the function cosine of x. After all, the span of a collection of vectors is just the linear combinations of those vectors. So I'm thinking about vector spaces that are built with functions instead of column vectors now. I want to be able to say that the set of every solution to this equation can be built by taking combinations of these two. Another way of saying that is, I would really like to know that this is a basis for the space of solutions. The problem with all of this is that I need some notion of linear independence that works here. I need to know if I'm going to be using these two things to construct my set of all possible solutions, that I'm not just repeating myself, that I have enough information to describe all of it. So I need some way, I need a notion of linear independence of functions. So now, functions are going to be vectors. Functions are vectors. And they live in a specific vector space when we're talking about differential equations. A vector space of functions is what's called CKI. This is the set of k times continuously differentiable functions. In fact, we've already spent some time hanging out with a version of CK. When we were in 241 and we were doing Clause's theorem, when we were talking about the second derivative test, the mixed derivatives, we looked a lot at the space C2. C2 was the space where fxy was equal to fyx. In your engineering and science classes, normally what people do is they say, assume sufficiently nice functions. And what they mean is, live in some version of CK where k is just as many derivatives as you need to make everything cool. So C2 and C3 are pretty typical.
Is that C2?
It's C2, you should think C2 leads to. In C2, it's the case that fxy is equal to fyx. This is the space on which Clause's theorem held. Twice continuously differentiable functions. It occurred to me in the last class that you guys maybe have never seen a function that doesn't have a continuous derivative before. So I thought I would write down a function that has a derivative that is about, if you plot it in Desmos, you're going to find that it's got the worst derivative in the entire universe. So here's an example of a function that does not have a continuous derivative. An example of a differentiable function that does not have a continuous derivative. All right, so this is one of my favorite terrible things here. I mean, all bad things are good, right? So think about the function f of x is equal to x squared times the sine of 1 over x. This is the sort of function that engineers and scientists want nothing to do with. Plot that bad boy in Desmos, and then plot its derivative in Desmos. So this function has this graph. It's sometimes called a topologist sine curve. So it's trapped inside of these parabolas, y equals x squared and y equals minus x squared. And this part acts like a sine, but as it gets close to 0, these values get larger and larger and larger. So this thing kind of comes in like this, where it's going really slow, but the closer to 0 it gets, the faster it goes. Oftentimes this is shown to people where you zoom in your calculator and it never gets any better. It just stays equally terrible no matter how much you zoom in. So this is a function that is continuous, because it clearly limits to 0 at 0. So you can just fill in the hole. It's not defined at 0, but you can fill in the hole with 0. The derivative actually turns out to exist everywhere. But the derivative can't be continuous because the slopes are getting close to infinity as you come in from the left and the right here. But if you actually wrote down the definition of the derivative at 0 is 0. So this is a function that's differentiable everywhere, but the derivative isn't continuous. And that's pretty terrible. So why do we, one of the things that people ask about why we even care about this space is that if I'm not restricting myself to certain levels of smoothness, I admit things like this into the realm of functions that I have to consider. And I don't want to do that, so I just eliminate that by saying, okay, C2 means that's not part of it. Throw it away. And this is like the life of an engineer. It's essentially throwing away the stuff that sucks, right? Okay, so don't worry, I won't ask you any test questions on that thing. Although, if you want to play around, I've got all kinds of terrible questions to ask about that bad boy. So here's a definition of linear independence. So let's suppose that we have functions f1, f2, f3, up to fk in the space ck minus 1 on some interval I. Remember, all that means is I can take k minus 1 derivatives of these things. Yeah, there's no f0. There's just a list. I'm going to need the k minus 1 derivatives because I'm going to define the Wronskian, and I only need to take k minus 1 derivatives of k functions. Then we say f1 up to fk is a linearly independent set. In fact, you should be able to predict this. If C1 F1 plus C2 F2, I should put some X's in here so we really emphasize. C1 F1 of X plus C2 F2 of X plus CK Fk of X is equal to 0 has only the solution C1 is equal to C2, all the coefficients have to be equal to 0. That's just like when we did this for vectors, except with one more obnoxious condition. That has to be true for every single x in the identity that you're defined on. So you have to check not just a single value of x, but all of the possible inputs. This is essentially an impossible condition. Well, I'm immediately going to teach you the tool that you use to get around this problem, right? So the thing is now, if I write down the definition of linear independence, and I give you two functions, that definition would imply the following. If I ask the question, are sine of x and cosine of x linearly independent? You, from the definition, would have to answer this question. Oh, I need to show that C1 times the sine of x plus C2 times the cosine of x is equal to 0 has only the solution C1 is equal to C2 is equal to 0 for simultaneously every x. So you pick a C1 and a C2, you have to check every x for that C1 and C2 that question is impossible. And how do you know? I mean, these things are moving around. The x's are changing the values of the functions. So I don't know how to do this. If only there was a better way. So some of you may have noticed that when I assigned the homework, I accidentally assigned problem 24 from section 4.6 or something about linear independence. And then I asked you to show that three functions were linearly independent. And you went and read the chapter, and it had this thing called the Wronskian in there. So let me actually teach you what the Wronskian is, because this is where I wanted to do this. So the point now is, I want to be able to say that those vectors are linearly independent, because I want this combination of those vectors to be two-dimensional. I don't know. But remember, I have to be able to pick the C1 and C2. So this is, the definition of linear independence is harder than you're thinking. So I'm going to give you an equivalent condition. If you've read ahead in the book, and you thought to yourself, wow, the book is really doing a lot of stuff out of order and moving really quick, I guess that will, since I don't identify the book, I'm happy with that being in the video, I suppose. All right, so here's the definition. I'm going to do this definition in two variables because it's easier to write down. So, given two functions, f1 of x and f2 of x, the Wronskian, I should spell it so you guys all have this when you go home for summer. You can talk about what you learned. You learn about the Wronskian. Oh yeah, the Wronskian of f1 and f2 is a function, w of f1 and f2. It's a function of x. And the way that you calculate it is the determinant of this matrix where you put the functions and their derivatives inside of it. I mean, you could actually calculate it in this case. This is going to be f1 times f2 prime plus f1 prime times f2. So by way of example here, if I calculate the Wronskian of sine and cosine, the Wronskian of the sine of x and cosine of x as a function of x is the determinant of the matrix where I write the sine and cosine down, and then I write their derivatives. And now I calculate a determinant. Minus sine squared of x minus cosine squared of x, which is -1. Did I blow something? Oh! Yeah, determinants have negatives in there, yeah. I wrote it over here correctly. Okay. So you might ask, well, what use is that? Fine, you made up something, you calculated a determinant, you took some derivatives. So when you guys were doing your exercises on linear independence or dependence of column vectors, one of the tricks that the book showed you was if I gave you 3 vectors in R3 and I asked if they were linearly independent, you could put them in a matrix and take the determinant. And if the determinant was 0, they're dependent. And if the determinant wasn't 0, then they were independent. That is what this gives us for functions. The Wronskian acts like a check for linear independence. So the big theorem here is going to be a big theorem. So the big theorem here is if the Wronskian of f1 and f2 as a function of x naught is not equal to 0 for a single value of x naught. If I can find any value of x naught on which that Wronskian is not 0, the functions are linearly independent. If the Wronskian of f1 and f2 of x naught is not equal to 0 for at least one value, x naught, then f1 and f2 are linearly independent. So the Wronskian is basically a formula for checking to see if these things are linearly independent. I'm sorry, I wrote that down so far on the board. Let me write it up here again. If w of f1 and f2 at x naught is not equal to 0 for some x naught inside the interval you're working on, then f1 and f2 are linearly independent. What that means, yep.
So it can't equal 0 for any.
There just has to be one place where it's not 0. Remember, the original condition was I had to show that solution held for every single x, but the Wronskian lets me sort of cheat mode my way into if there's a single place where it's not equal to 0, then they're linearly independent. So the problem we just wrote down, the Wronskian of the sine of x and the cosine of x as a function of x was -1, which is not 0 the last time I checked. Nope. Not a very interesting number system if -1 is equal to 0. And that implies that sine of x and cosine of x are linearly independent. Now I'm going to bring some linear algebraic terms into the mix here because the reason we learned all the linear algebra was so that I had notions of things like span and dimension available to me. So as soon as I have the fact that these two vectors are linearly independent, then that also means the following. The span of the two vectors, sine of x and cosine of x. Well, if they're two linearly independent vectors, that's a two-dimensional vector space. Yep.
Can you like write cosine out of sines then?
But the way to think about that is you can, but it's a shifted cosine, right? So it's not actually, sine and cosine aren't equal to each other. There's a phase shift involved there. So you're actually, you can think about that as getting, one way of thinking about what it means to be linearly independent as a function is that you're getting two different types of information from the function. So sine is an odd function, which means it's symmetric around the origin. And cosine is an even function, which means it's symmetric around the y-axis. So they're picking up two different types of information when you put them together. You can manipulate one into the other, but only by phase shifting the cosine to do it. Right? That's basically that's basically the picture. And the phase shifted cosine and the original cosine will also turn out to be linearly independent.
Okay.
You have a question, Arlo, or are you just like fixing your hair? Okay. So now we're armed. We've got the idea here that I can use the sort of linear algebraic idea to check for the linear independence of these functions, and I'm going to be able to build solution spaces to differential equations where I have exactly the right of information and no extra. So I will know when I have enough information to solve a differential equation. So that's kind of I'm going to try to convince you that that's the game over the rest of the class here today. So let's talk about 8.1, which is called linear differential equations. This is going to be our object of study basically for the next week and a half. Other than the fact that you guys have a midterm next week. But yeah. Minus that part. Okay, so a linear differential equation, examples of linear differential equations look like this. So y prime prime plus xy prime plus cosine of xy is equal to 0. That is a linear differential equation. 2y double prime plus 3y prime plus 6y is equal to 0. That is a linear differential equation. I'm going to define this in a second. Y times y double prime is equal to 0. This is linear. This is linear. This is not linear. So when you're thinking about linear equations, what I want you to think is it's linear combinations of the derivatives of y. So I can't have products of the derivatives, and I can't have powers of the derivatives. Linear combinations of the derivatives of y. Every single type of differential equation that has that feature is called a linear differential equation. So y prime prime minus 2y prime minus 15y is equal to 18e to the 6x, the example that we started with, is a linear differential equation because it looks like a linear combination of the derivatives of y. In fact, we could put lots of adjectives on this differential equation that I can remind you of. The first is, it is called a linear differential equation because it's a linear combination of the derivatives of y. It is also second order because there's a second derivative. It is constant coefficient because all of the coefficients here are constants. The things we've multiplied the derivatives of y by are not functions. And then finally, it is non-homogeneous. Because there's some stuff over here that's not 0. So basically, the study of differential equations boils down to throwing enough adjectives at the problem that you know what to do. So I'm going to be more formal about what I mean by a linear differential equation now. Because I think this is a place where the book kind of goes over the top with notation, and I want you to be able to read the book to figure out what the hell it's talking about. So the first thing that we do when we look at linear differential equations is I'm going to come up with a piece of notation that makes it easier to write down. So we're going to let the symbol d mean the act of taking a derivative. This is sometimes called a differential operator. You can think about it as like a matrix that you're going to apply to a function. So d squared, when I write that, I mean take two derivatives. D to the third would mean take three derivatives, and so on. So if I wrote d squared y plus dy, what I mean is, so I can think about it as being d squared plus d applied to y. What I would mean by that would be y double prime plus y prime. So this is the book's notation for writing these derivatives. Like, it likes to use this operator notation because it can treat it like something that you can factor the y out of. So, when the book writes down a differential equation, what it likes to do is to say, oh, if you had the differential equation y prime prime plus y prime is equal to 0, the first thing it's going to do is rewrite this as d squared y plus dy is equal to 0. Then it's going to factor the y's out. And that object right there, that d squared plus d, it's going to call that L. If you've been reading the book and you're trying to figure out what's going on with all the d's and the l's, it's saying L is some kind of polynomial expressed in terms of these derivatives. So these are all notations for the same thing. Y double prime plus y prime is 0, d squared y plus dy, d squared plus d applied to y, or Ly is equal to 0, where L is equal to d squared plus d. All the same. The differential equation is called linear. It's linear if it is of the form a naught of x, yn plus a 1 of x, y n minus 1, plus a n minus 1 of x, y prime, plus a n of x, y is equal to f of x. Now that looks like a giant pile of notation. All it's saying is it's a linear combination of the derivatives of y. That symbol right there means the nth derivative of y. So it's just telling you linear combinations of derivatives. But the coefficients can be functions. Functions of x. Yep.
Does it have to be every derivative? Like
No, those could be, you could have zeros in there.
Okay.
So a good example of that might be something like y double prime plus y is equal to 0 is a second order linear differential equation, even though there's no y prime here. This is actually a very common sort of differential equation. So in fact, if you guys have ever seen harmonic oscillators in physics or your engineering classes, all of those oscillators come from equations that don't have prime terms. Okay, so the other way that the book would like to write this would be, I think in its definition it says, the differential equation is linear if it's of the form Ly is equal to 0, where L is given by a naught d to the n plus a1 d to the n minus 1 down to a n minus 1 d plus a n. It's the same thing. It does not have to be, oh, sorry, f of x. Yeah, I had the f of x up here. Yeah, so this is homogeneous, non-homogeneous. The linearity comes from the left-hand side, not the right-hand side. Okay, so let's talk about the solution space to a differential equation, a linear differential equation. Now that we've got linear differential equations, here is the sort of big theorem. I was going to prove this, other professors do. I might fan this for now because I think it's this is already going to be a lot of theory and vocabulary today, so I'm just going to tell you the theorem. The idea of this theorem is really easy. An nth order differential equation, so this is a theorem called the structure of solutions. An nth order linear differential equation that is homogeneous. That is to say, we're looking at something of the form of the form the nth derivative of y, the n minus 1th derivative of y, n minus 1 y prime plus a n y is equal to 0. Well, being a little careful here, you might notice I didn't put anything in front of the yn term here. There are reasons for that will become apparent if you continue on to 344. So an nth order linear differential equation that is homogeneous, that has this form, where there's nothing on the yn term, has general solution y is equal to c1 y1 plus c2 y2 plus cn yn, where y1 through yn are linearly independent. It's worth taking a moment to see what that actually means. That means if I give you an nth order equation and you find n linearly independent solutions, you found all the solutions. You could just add them together and you got all of them. If you got a second order equation and you get 2 independent solutions, you have solved the equation. So, this implies the solution space to something like y double prime plus y is equal to 0, the space of all possible solutions to that differential equation is 2-dimensional. The number of linearly independent vectors that I need to describe the solutions is equal to the order of the differential equation. It's order 2, so the solution space is 2-dimensional. So if we go back to what we started the class with, when I'm talking about sine and cosine here, we have shown already y1 is equal to the sine of x and y2 is equal to the cosine of x is a set of 2 linearly independent solutions. To y double prime plus y is equal to 0. I've already got 2 of them. The theorem here says that there is exactly a 2-dimensional solution space, but I have 2 linearly independent solutions. So by invoking linear algebra, that must mean, thus, the set of all solutions to y prime prime plus y is equal to 0 should be the span of sine of x and cosine of x. These are linearly independent. That is a 2-dimensional span. If you don't like linear algebra, instead you could say that the general solution, so So this is like sort of the linear algebra version. If you want less linear algebra in your life, you can say instead, it must be that the general solution is y is equal to c1 sine of x plus c2 cosine of x. I want to reiterate here. What I'm saying is a second order equation, when you find two linearly independent solutions, every other solution must be a combination of those solutions. It has to be. So the game of all of this linear differential equations is going to be, I give you an equation, discover enough linearly independent solutions to describe all the possible solutions.
Are we gonna find the base too of these, or just the span?
What do you mean?
Like, is that also the base?
This is the basis right here. This is the basis, right? This is a linearly independent spanning set for the solution space, right? So yeah, this is actually why we did all that, learned all linear algebraic vocabulary. Yet another way of saying this is sine of x and cosine of x are a basis for the solution set or solution space. I like linear algebra, so again, the more of this language we can get in here, the better. All right. So, one way of thinking about where these things come from would be if I wrote down y prime prime minus 2y prime minus 15y is equal to 0, I think I wrote down earlier that equation we didn't eyeball, I just told you the solutions. So we're going to guess what the solution to that is. We're just going to guess. But we're going to get our guess by looking at this equation. If I wrote down y prime minus 5y was equal to 0, what would the solution to that differential equation be?
E to the 5x.
Sure, that does it. Y prime is equal to 5y. So a function that's equal to the derivative is 5 times the original function is definitely y is equal to e to the 5x, right? That works. What if I wrote down something like y prime minus ry is equal to 0?
E to the rx.
E to the rx will do that. Y is equal to e to the rx, because y prime is equal to r e to the rx, and if you plug this in here and you multiply this by e to the rx, you get 0, right? So these simple linear differential equations have exponential solutions. So now we're going to do the most applied mathematics thing or engineering thing of the entire day so far and say, what do you do? What do you do when you don't know what to do? You just guess. No. There's no derivatives. We're going to look at that. Thinking derivatives is going to make this worse. I got y triple primes running around, right? Well, I can't integrate it because I don't know what the function is. And the integral of y will be something called like the antiderivative of y, which is going to be even worse. No, this is even dumber than that. We're going to say, well, exponentials solve these equations, and this kind of looks like that. Maybe exponentials solve that equation too. We're going to formalize the idea of constructive guessing in chapter 8.4. So we're going to look at something that the book calls a trial solution. We're just going to guess that the answer to this must look like y is equal to e to the rx. And we're going to see if plugging in y equals e to the rx into that equation gives me something sensible. After all, exponentials solved equations that look like this. Maybe they do it here. There's hundreds of years of practice in just guessing the answers to differential equations at this point. So this is a time-honored tradition. Y prime is equal to r e to the rx. Y double prime is r squared e to the rx. If you take that information and you plug it back up into this differential equation, you get, okay, let's see. So, I don't know, your neighborhood math professor tells you, maybe you should try this trial solution, and you plug it in. You get r squared e to the rx minus 2r e to the rx minus 15e to the rx is equal to 0. So remember, we're assuming that this is a solution, which means we're assuming that equation is true. For that to be a solution means it solves that equation. So we're assuming this is true. I can factor out an e to the rx. What would it take for that equation to be true? Well, can e to the rx ever be 0?
No.
It's an exponential function. So just throw it away. You guys like to divide things out of quadratic equations or whatever. You can actually divide because this is never 0, so you just chuck it. That's going to be equal to 0 whenever this is equal to 0. Now, I recognize that for a lot of you, it's been a long time since you got down in the mud with quadratic equations and factoring them. There's going to be a whole lot of this going on the next couple of days. Quadratics, cubics, all this crap. So if you need to re-hone yourself on how to eyeball these things, I will do my best to make these things.
5 and
Yes,
negative
this
3.
one is set up negative 5
Exact
and...
op- Our solution is 5 and negative 3.
5 and negative 3.
No, after negative 2.
R is 5. Let me remind you that if it's been a while since you've done this factoring, that you might revisit these things because we're going to be doing a lot of it. R is 5 or R is
I
negative
was
3.
stating something different. I was
Yeah,
saying-
believe
I wasn't talking
Put your
about
pitchforks down. All right. Okay, or oh God help you if you're just like going to dive into the quadratic formula. Then you guys want to simplify your answer into carrying things around like the square root of 25. Like, anyway. Like, oh, I'm just going to carefully blast through an entire equation with e to the minus the square root of 16t or something. No. Anyway, so remember that we assumed that this was a solution to the equation, which means it actually was. This is equal to 0 in the specific case that r is 5 or r is 3. So what that sort of conclusion is, since our trial solution was e to the rx, that means that what we've discovered is actually we were right. y1 is equal to e to the 5x, and y2 is equal to e to the minus 3x. Those are two different solutions to the differential equation. We guessed correctly. We got an equation we could solve. We guessed correctly. Those are our solutions. Now the next step is to say, did we get all of the solutions to the differential equation? So when I look at, hold on, Azealia. This is a rhetorical question. When I get to the real question, I'll let you know. So, okay. So I know now that differential equation has at least these two solutions. If I want to conclude that I've got all the information I need, what do I need to know about those functions?
Linearly
They better be linearly independent. How am I going to check that? The Wronskian, that's right. So let's calculate the Wronskian of e to the 5x, e to the minus 3x. So we're going to calculate the determinant of e to the 5x, 5e to the 5x, e to the minus 3x, minus 3e to the minus 3x. If you do that determinant, so e to the 5x times e to the minus 3x is e to the 2x. You get minus 8e to the 2x. Can that ever be equal to 0? No, if you're going to learn anything, remember anything from this part, it's exponentials don't cross the x-axis, right? So this is never 0. And that means that's a linearly independent set. So now you have e to the 5x, e to the minus 3x as a set is a linearly independent set of solutions. Write the general solution. Man, this is like
Well, did
decibels,
you,
but
like,
no,
was it, like, a rhetorical question? Like, you asked a previously rhetorical
I
question.
did. I made that one deliberately vague, I guess, right? So, right. So the idea now is, do I have enough to? So the thing is, there's at least 3 different ways of saying what the solution set is here. So I want all 3. Okay, that's the sort of you hate linear algebra approach, right? The general solution y is equal to c1 e to the 5x. I'm not saying you hate linear algebra, but if you did,
Well, yeah.
then you would write that, right? You have enough linearly independent functions to know that you've described the entire solution space, because as soon as I have 2 of them for a second order equation, I have exhausted all possibilities. Every solution must look like that.
It's the span.
It's the span. Okay, second, it is the span of e to the 5x, e to the minus 3x.
Or it's the basis.
or it's a basis. Or you could say e to the minus 5x, e to the positive 5x, e to the minus 3x is a basis for the solution space. So we learned all that linear algebra and linear algebraic vocabulary because this is actually the way people think about it. People think about the structure of solutions to differential equations by thinking about vector spaces, by thinking about ideas like linear independence. There have been, this is one of these sort of disaster things that seems like a triviality until you think you've solved a differential equation and you didn't actually bother. So I give you 18 functions and I say, did you find all the solutions? And you don't check the Wronski and you just glue them all together, you might have missed something. If you didn't actually check your Wronskian of your 18 different solutions, there might be some solution that has some pathological behavior that you missed, and then your rocket explodes or your bridge falls down, right? Checking to make sure that you've exhausted the entirety of the solution space to a differential equation is really important in practice. Second order equations have two components to their solutions, and if you miss one, we'll see later, you guys know what resonance is or have seen videos of resonance, like bridges shaking themselves apart? If you miss a component of the solution that causes resonance, you've really done something wrong, right? And missing resonant frequencies is something that happens all the time in reality. So, okay, so I don't want to talk about it anymore today because I think this is enough. I will end with an anecdote about missing phases here. At MIT, I don't know, 30 or 40 years ago, the architects that designed one of the dorms, when they did their analysis of the structural analysis of the building, missed one of the resonant modes of the building. And the students that lived in that building built a gigantic speaker system in the stairwell and a sine wave sweeper that they went through where they just spun the sweeper through all the frequencies available until they found the missing resonant frequency. And they basically tried to shake the building apart with the speaker system. I didn't go to MIT.
No, but didn't the people live in that dorm?
Well, I want you to think about what you've seen in your time at Cal Poly and just imagine.
Go to someone else's dorm.
Well, I'm sure they were in somebody else's dorm. All right, I'll see you guys later.